Hello, everyone. Welcome to Introduction to Big Data. Big data is a term you've likely heard in various contexts, probably from everyday business discussions or conferences or from school and class. But what exactly does big data mean, and why has it become such a big popular topic in recent years? So, in this lecture, we're going to look at the foundational concepts of big data and discuss the reasons behind its growing importance and look at the transformative role it plays in modern organizations. We're going to look at some of the key technological tools that have emerged to handle big data, compare traditional data processing approaches with big data methods, and discuss future challenges and trends. Defining big data. So, big data is commonly described as data sets that are too large or complex for traditional data processing approaches. While the term big data might sound like a buzzword because um, it embodies the realities of handling massive volumes of structured, semi-structured, and unstructured data, data that arrives at a high velocity from multiple sources and in a different format. So over the past decade, the increasing digitization of everything meaning from social media interactions to IoT device sensors, it has contributed to an explosive growth in the volume and variety of data available. So companies with conventional database systems, they often find these systems inadequate for capturing, storing, and analyzing this uh, influx of information efficiently. So, this need for scalable, distributed, and fault-tolerant solutions has led to the development of new technologies and frameworks that power the big data revolution. The five B's of big data. So one of the most common ways to describe big data is through its V's. Initially, there were three, volume, velocity, and variety. Over time, experts have added two more important vectors, veracity and value. Uh, let's talk about volume first. Volume refers to the massive amount of data generated every second. You can think about the billions of social media posts or e-commerce transactions and sensor readings produced globally every day. Velocity, velocity is not just about having, big data is not just about having a lot of data, but also how fast that data is coming in. So high velocity data streams demand real-time or near real-time processing. Variety, so data can be in many forms. Structured data, what I mean by structured data, you can think of data in rows and columns, and unstructured data, such as images, videos, and text, and semi-structured data, such as JSON files or log files. Veracity, and this is about the reliability or quality of the data. Since big data comes from so many sources, We need to make sure that it's accurate, consistent, and trustworthy. Value. Ultimately, data is meaningless unless it's translated into insights that are actionable. Data can help organizations make better decisions, discover new business opportunities, and innovate more effectively. Evolution of data storage and processing. In order to understand why big data technologies evolved, it's helpful to look at back at how we manage data historically. Let's first talk about traditional databases, RDBMS. So for many years, relational databases like MySQL, Oracle, or Postgres, they were sufficient to handle most enterprise data. They store data in a structured tabular format. However, these systems often can handle the really large scale and varying nature of modern data sets. Second, data warehouses. So companies began using specialized data warehouses. You can think of Amazon Redshift, Teradata, and so on to aggregate data from different sources for analysis. And this approach allowed for better analytics, but still relies on structured formats, thus limiting its capacity to handle unstructured data at large scale. Distributed file systems, with the advent of Hadoop distributed file system and its ecosystem, organizations could store massive volumes of data cost effectively across clusters of commodity hardware. And this approach laid the groundwork for the modern big data revolution. Cloud-based solutions. So today, cloud platforms like Amazon Web Services, Microsoft Azure, and Google Cloud, um, they offer scalable and on-demand big data services. They reduce the barrier to entry for organizations of all sizes, enabling them to store, process, and analyze huge data sets without significant upfront infrastructure cost. Importance and use cases. Big data has become a critical component of how businesses and other organizations operate. And let's first talk about data-driven decision making. So instead of relying solely on intuition, organizations can use analytics to guide strategic choices. So for example, uh, a retail company can analyze purchasing patterns to decide which products to stock. Personalized customer experiences. Let's talk about Netflix. Let's think about how Netflix recommends shows based on your viewing history or how Amazon suggests products you might be interested in. And these recommendations are uh, powered by big data analytics models. Operational efficiency. Um, we can talk about manufacture as an example. So by analyzing sensor data from, say, factory equipment, manufacturers can detect and any issues and predict maintenance needs before a breakdown occurs, therefore saving time and cost. Predictive analytics. So this one, let's talk about finance as an example. In finance, big data models help institutions forecast market trends, assess credit risk, and flag fraudulent activities. And, and we can talk about industries. So big data is impactful across healthcare, finance, retail, telecommunication, transportation, and more. And each industry uses data for unique applications, from patient care improvements to real-time route optimizations for delivery trucks. Moving on, big data technologies. In order to manage and analyze big data effectively, the industry has developed a range of technological tools and frameworks, and some of the most prominent include Hadoop ecosystem. And when we talk about Hadoop ecosystem, we're talking about Hadoop distributed file system for storage, MapReduce for batch processing, and a Yarn for cluster resource management. Hadoop was one of the first open source projects to enable distributed processing of uh, vast data sets on commodity hardwares. Apache Spark. Spark is a fast and general purpose cluster computing system known for its in-memory computing capabilities. It supports batch processing, streaming, machine learning, and graph processing, and making it a versatile solution for many big data workloads. NoSQL databases, systems like MongoDB, Cassandra, and HBase, they are designed to handle large volumes of data that may be structured, semi-structured, or unstructured. They offer high scalability and flexible schemas, which can be crucial for real-time big data applications. Streaming platforms, tools like Apache Kafka and Apache Flink handle data streams in real time, making them essential for applications where low latency processing is a priority, like real-time analytics dashboard or fraud detection. Lastly, distributed computing platform frameworks. So beyond Hadoop and Spark, there are many distributed systems that enable parallel processing across clusters, and these frameworks are key to scaling big data workloads efficiently. Traditional versus big data approach, when we look at how data was traditionally handled, data is traditionally handled using a single powerful server that runs um, a relational database system. And this approach can become really expensive and inefficient once data grows beyond certain threshold. So let's first talk about centralized versus distributed. Traditional systems often rely on a single machine or sometimes a small cluster of specialized high-end machines, whereas big data systems distribute storage and processing across many servers that are commodity level. Scale up versus scale out. In a traditional environment, you typically scale up by adding more CPU, RAM, or disk spaces to a single machine. In big data, you scale out by adding more servers to the cluster, which is usually more cost effective and flexible. Structured versus unstructured. Traditional systems often require data to be Structured in a rigid schema, big data solutions can handle data in its native format. And native format can be text logs, sensor readings, images, or other types. Batch versus real-time processing. Historically, data was processed in batches. You can think of like end-of-day reports, and big data technologies now enable near real-time analytics, which can be crucial for organizations that need to make decisions immediately. Real-time, real-world implementation examples. First, social media analytics. So platforms like Facebook, Twitter, and Instagram, they generate petabytes of data daily, and they use big data analytics to recommend content, detect spam, and improve user engagement. E-commerce personalization. Amazon is famous for its recommendation engine, and its recommendation engine personalizes product suggestions for each user. And this can be done by analyzing a user's browsing and purchase history along with data from similar users. And by doing this, Amazon can significantly increase sales through targeted recommendations. Predictive maintenance. Companies like GE collect data from sensors embedded in industrial equipment, and this industrial equipment could be turbines, engines, manufacturing robots. By applying predictive analytics, these companies can anticipate failures before they occur, thereby reducing downtime and maintenance cost. Smart cities. Urban areas are integrating data from traffic lights, public transport systems, and energy meters to optimize resource uses, manage traffic congestion, and reduce environmental impact in real time. Challenges and future trends. While big data offers many advantages, there are also significant challenges and evolving trends. First, data quality and governance. With large amounts of data coming from different sources, in ensuring consistent quality, removing duplicates, and establishing governance frameworks is really important for having reliable insights. Security and privacy. The more data an organization collects, the more it must protect. Data breaches and the misuse of personal information are major concerns. Regulations like GDPR in the uh, Europe underscore the importance of compliance in data handling. Skills gap. So big data involves complex technologies, but also big data requires skilled professionals. Skilled professionals such as data scientists, data engineers, and data analysts who can build and maintain big data infrastructures and models. And there is a shortage of skilled professionals. Growth of AI and machine learning. As data sets grow larger, uh, these advanced analytical methods become more powerful. Big data and AI, they feed each other. AI models usually need massive data sets to learn effectively, and big data systems help store and process those data sets. Lastly, edge computing and IoT devices like smartphones, wearables, and industrial sensors are generating data at the edge. Instead of sending all that data to a central server, we can process it locally for real-time insights, which reduces latency and network usage. Conclusion, let's do some recap. So big data refers to data sets that are too large, varied, or fast changing for traditional technologies to handle effectively. Importance and business across industries leverage big data to make better decisions, predict future trends, and personalize user experiences. In terms of technology ecosystem, frameworks like Hadoop, Spark, and NoSQL databases form the foundation of big data architectures. Going forward, big data will continue to shape how we innovate in everything from personalized healthcare to autonomous vehicles. So the potential to derive insights from data is practically limitless. Thank you everyone for listening to this lecture.